also recommend listening to or reading this topic from maybe one or two other sources, the textbook and then like Khan Academy or something, because it is very useful to hear it said a few different ways before it sticks in your brain. So all the stuff that we've done up until now, I would say there was at least some connection. There still is a connection to the real world, but much less so. So there's been some connection to the real world. You're like, oh, I have some powder that I'm going to measure out the number of grams, right? Then we do some funny things with it and we convert it to moles, and that was a little bit weird. But I think a lot of the stuff we could conceptualize quite a bit easier. And this stuff like breaks people's brains even that have been studying it for years and years, okay? The reason is because the concept of quantum mechanics, the theory of quantum mechanics, has no consistency with our macroscopic scale. So I will say that a couple times about macroscopic universe. What I mean is like I have a particular mass, and if maybe I'm not a good example because I won't fall down. My phone has a particular mass, and if I drop it, gravity is going to act on it in a particular way. Or if I throw a ball, it's going to behave in a particular way. If I'm looking at the ocean and it's moving like this, like a wave, it behaves in a particular way, okay? Things on the atomic scale, so we're talking electrons, how they interact with the atom itself, how they interact with light. So light is the type of energy we talk about when we talk about energy interacting with atoms. How light behaves, those are atomic scale things. And they do not seem to follow the rules of macroscopic scale, or at least they have their own tinier subset of rules that they follow. So it is very difficult for us to conceptually understand how they behave when we can't make an analogy to the macroscopic scale. That is why it hurts people's brains when we talk about this. The reason that, do I want to go there first? The reason that we have to talk about it is because quantum mechanics, which I think actually I have, there we go. It's not showing up on my screen. Let me reload that. Okay. So I'm going to say a lot of the things up here, but not obviously read them. But last class I was on the front screen and then said a bunch of stuff, and then I was like, oh, it's all right there. So we'll put that up while I'm talking. Everything in quantum mechanics, which again is going to describe the behavior of electrons. Why do we care? Because electrons and how attracted they are to their atom, or how attracted they get to another atom, that's all that dictates chemical behavior, okay? All of that stuff is what our modern society is built on. So quantum mechanics started getting developed in the late 1940s and 1950s. So it is really, really recent, like 75 years old. If you can think about the timeline of technology, shortly after that is when we started having computers developed and microchips, and it's just kind of taken off from there. So it is essential to all of those kind of technologies. They are all built off of this understanding of the electron and how it behaves, okay? So that is why it is so crucial, and we are just gonna barely scratch the surface of it to hopefully give you guys a basic understanding of how these things work, mostly so that if you go like study or read something else, like let's say you're going into like an engineering field, you need to have an introduction to this stuff so that then you can take it in the direction that's necessary for your field of study. Or when I'm teaching a freshman class, I like to think of it as just general scientific literacy. If you read some news article about like quantum computing, I would like you to have just the semblance of idea of what they're talking about when they talk about quantum, okay, or quantized. So that's the idea today. We are literally like reading the introductory chapter of a quantum mechanics textbook, okay? So it's very overview, but still very important for you to understand, okay? The other thing that's cool is that we're going to talk about in chapter 9, We're going to talk about like the size of atoms, how good they are at attracting other atoms, how they'll bond, and this stuff explains all of that, okay? So the main things that this is going to provide for us is talking about the location, we're going to say, and that ends up telling us about the energy of the electrons in the atom. And why is that important? Because that dictates chemical behavior. Lots of times people are like, chemical behavior, okay, so like how to make plastics, how to make drugs. No, computers are all based on chemistry too. Solar panels, that's all based on chemistry as well. So that is all based on this stuff. That's such a chemist point of view of saying, like, it's all chemistry. A physicist will be like, well, quantum mechanics isn't even chemistry in the first place, it's physics, so whatever. Okay, so we're going to start by talking about light. This always bugs people because they're like, why in the world are we talking about light and energy when you just said we're talking about electrons? Well, one reason is because the way that we probe electrons, like understand what they're doing, and also manipulate them is by putting energy into them in the form of light. When I talk about light, I am not talking about just visible light. That is a small fraction of what we're talking about. So if you have never seen something like this before, this is what a chemist or a physicist, or maybe even a biologist, is talking about when they talk about light. They are talking about all the different kinds of energy that fall in what we call the electromagnetic spectrum. Okay, and visible light is this tiny part of it that we can see. So you can have everything from like, you know those like laser pointers that aren't actually laser pointers? Maybe that's a bad example. Ooh, laser tag. My kids just ordered laser tag and I was like, oh my gosh, are they gonna hurt someone's eyes? Because like laser pointers can actually damage your eyes. So I looked it up and it's like, oh, it's not actually laser, it's infrared light, okay? So they're like running around the house and they shoot their laser gun at the other kid and you can't see anything, right? But it somehow registers on their little target. That's because there is energy being sent across the room, but it's not visible. It's in the infrared range. So that's a great example of energy that, does something. It must have an effect because the little sensor registers it, but it's not visible to you. I used to use the example of a dark room, like where you develop photographs, which was like a class when I was in high school. Like that was an art class. You could take photography. That's not a thing anymore, I don't think. Maybe a lot of artists, maybe some artists still use it, but obviously not something you guys would have experience with. But in a dark room, you use light bulbs, but they only emit red light. And I guess the analogy here that would be good is you guys probably know enough about like blue light exposure. Like you're not supposed to have blue light at night because it's stimulating and it'll keep you awake. So like on your phones a lot of the time, it'll shift the coloring. It does it automatic on some of it you have to sense or like put it in the settings. But mine does it at 7 p.m. Like I have it on a schedule. So literally if I'm looking at my phone at 6:59, it will shift and have this orange undertone so that I'm not getting as much blue light at night. That's because orange light, red light, is lower in energy than is blue light, and it has less of a stimulating effect on your brain, okay? So even just different versions of this can have, real life effects. You could like look at individual light bulbs if you think of like party lights, like Christmas lights, that have red or rainbow colored lights. Those are just using different wavelengths. We're going to talk about that in a second, or different energies of light. So that's all in this visible area. There's all these other types of light. I just talked about infrared. Microwaves. A lot of people are shocked that that's the same thing as visible light. It just has a different energy. So all of its properties behave the exact same way as visible light, but at a lower energy range. There's a little bit of details into that as to why they heat up your food, but I'm not going to get into that right now. Radio waves, that's also a type of electromagnetic energy. They have I'm not going to talk about wavelength yet. They have very low energy. So like there's no problem with the fact that they're like constantly floating through the air, and you can turn on your radio and receive those radio waves because they're not going to hurt you because they're extremely low in energy. Okay? When we get on the other side of visible light, ultraviolet, so a good way to remember this, you don't have to remember any of the numbers. If I needed you to use the numbers, I'll give you this image. But you should have a general idea of the different types and kind of where they fall in regards to how low or high in energy they are. A good way to remember it is infrared is on the side of red, and we know infrared isn't going to hurt you, so it must be on the low energy side, so red is on the low energy side. Then you look at all the rainbow, you get up to violet eventually. That's your highest in energy. A good way to remember this is it's right next to ultraviolet, which this is sunlight. Sunlight comes visible, probably some infrared too, but visible and ultraviolet. The visible light from sun is not what's causing a sunburn, it's the ultraviolet. That's why it's higher in energy, because it can actually cause damage to your skin. You go even higher, now we're talking about x-rays. When you get an x-ray, a lot of the times they like cover whatever they're not x-raying in a lead apron or whatever, okay? So all of these different types of things have all of the same properties and behavior as visible light. We just can't see them with our eyes, okay? Infrared, another interesting one of that is like night vision goggles. So infrared is often associated with heat. So like a living object is going to emit infrared. And so if you're at night and you can't see anything, you can wear the special goggles. It registers the infrared light just like the laser tag would, but then it turns it into an image for you so that you can see what's going on. Okay? Okay, so why in the world are we talking about light? Like I said, light is how electrons will absorb energy and how we can manipulate them and how we can look at their properties. And soon we are going to realize that there is an inherent connection between light. So energy here, we're going to talk about that as light. And this equation, which I'm sure, you know, it's such a part of pop culture, you guys probably have never actually understood what it means, is my guess. But what it is showing us is that energy, or light, has an inherent connection to matter. This represents mass, the M, but we're going to just say matter, because if it has a mass, it's behaving like matter. Okay, so think atoms or electrons or protons or neutrons. All of those could have a mass and behave like matter. Okay, what this equation is telling you is that there is an inherent connection between light, energy, and matter. Really, what we mean is that we can actually convert, maybe not us usually, but things, matter, and energy can be converted from one to the other. That's the first time your brain should explode a little bit. What? How can you convert matter to energy? That doesn't make any sense. Okay, so let me give you an example of it. In a particle accelerator, if you've ever heard of a particle accelerator, there are these massive tubes. Usually they're built in circles, and we're talking massive like they take up like 20 acres of land. So they're running on the perimeter of this 20 acres. These huge tubes, and they take particles like protons and they shoot them at each other to see what happens. Okay, so if you take two protons and they each have a particular mass and you shoot them at each other and you get them to bond to now form helium, basically the nucleus of helium, two protons, they will exhibit, and then you go weigh that thing, they will exhibit a mass that is less than when they were separate. So like if they each had a unit of 1, when they come together, they will look like less than 2 units of mass. That is weird. It's very bizarre. what's happening there is that when they come together, they release energy. Where did that energy come from? It was converted from the mass. Some of the matter in the two protons actually got converted into energy and then was given off. So this is like a very basic example of how matter can be converted into energy. That should feel weird, okay? That's like, I don't know, you're like, is my body gonna turn into energy at some point? I don't know, maybe if it was in the right circumstances, sure, okay? So that is another reason why we talk a lot about light, is because although in our macroscopic world, we're used to thinking of light and energy as totally different than matter, when we start to look at them, especially on an atomic scale, they are not all that different. And they actually end up sharing a lot of properties that are similar. So we start by talking about energy for that reason, light specifically, okay? As you can already tell, there's a lot more concepts in this chapter than math. I am going to give you 2 equations today, and then I think 1 on Wednesday, and that will be all of the equations for the rest of the semester, okay? So very little math. There's going to be some doing. So like, remember how when we did naming, it wasn't actually math, but it was doing, like, oh, CO2, carbon dioxide, right? So there's going to be stuff like that that isn't math, but is doing. But all of that doing is going to be based on these concepts. So you are going to have concept questions. You'll have a very few number of math questions on the exam I'm talking about. And then you will have a lot of doing that's based on the concepts. Okay, so that's why it's important for you to understand this stuff. So if it's feeling weird and you're like, I don't understand what she's saying, try listening to the video again that I'm going to post on YouTube. Try listening to somebody else's description, like in the textbook, or maybe even go out to an online source, like a reliable one, like Khan Academy. Okay? All right, so light. Let's talk about the properties of light. So light exhibits what we model light or look at light as the same thing as a wave, like an ocean wave. So picture a little further out in the ocean, not by the beach, and you've got waves, okay? And they have a particular, what we say is wavelength. So I'm gonna look just at this red one here. So think of this as an ocean wave. And if you were to measure those waves, you would see that they're fairly consistent between the peaks, at least far out in the ocean, not by the beach. So you could measure the distance between the peaks, and we would call that the wavelength. This is how we model light, and by model, I mean scientists are always trying to come up with a way to think about an actual concept. And usually we compare it to something in the real world, okay, like the macroscopic world, like I was talking about before. So when we talk about energy, and specifically light, for the longest time, we only compared it to physical waves, like waves in water. They have a particular wavelength. With light, though, that wavelength is going to correspond to their energy. So let me show you the other ones now. So we said, I'm going to add to this. We said that red light was lower in energy than blue or purple light. So I'm going to write this in. Red light, lower energy, and blue is higher energy. And then let's look at their wavelengths. So the wavelength of red light is longer, even though the energy is lower. So this distance from one peak to another, or you could do from one trough to another, those would be the same. That distance is larger in lower energy light, whereas in higher energy light, these waves are shorter or closer together is the way you think about it. Okay, that wavelength is smaller. So I have that written down over here. Shorter wavelength corresponds to higher energy. On that chart that we looked at before, you can also see it there because they label the wavelengths here. And in this, they just give it in like 10 to the whatever. So they're saying, is it like 1,000 or is it 0.1 or 0.000001? Okay, so these are smaller wavelengths but higher in energy. Yep.
So I see like those red lasers normally leave, and if you have like purple lasers that light stuff on fire.
Yes, that would be true. Now lasers are a little bit different. They are laser light amplified stimulated emission radiation. So there's this technique that's used to make lots and lots of the light be really, really concentrated. But you're right, if it was a red laser, it would be lower in energy than a purple one. Exactly. Okay, so there's this one other property that we use to describe waves, and it's called frequency. So I have a description of it right there, but I'm going to show you on the wave what it physically means. So frequency, it says it's the number of waves that pass a point in a given time. So the units we use for this is probably the easiest to understand is cycles per second or waves per second. So if I look, these are moving, just like waves in the ocean. So if I look at this particular point and I let this wave move past this particular point, ooh, I should totally have, I bet you I can find a simulation of this really easy. But I look at this wave moving past this point, I'm gonna count every time a peak hits it, okay? So it's like 1, and this is gonna move and hit 2, 3, 4, and you would count how many times a wave goes past that particular point. So we say it's like how many waves in a given second, but usually you just write it as 1 over second. You'll kind of eliminate that waves part because everybody knows that's what we're counting. Mathematically, 1 over something is the same as that thing to the -1. It's called the inverse. Okay, so you'll often see the unit written as that. It means 1 over seconds. And then, of course, we have to give credit to the person who developed it, hertz. So we call this, we say that is also equal to hertz. Or, I don't know why I'm rewriting it. It's just up there. But all these different units mean the same thing. And that's how we describe how many waves would pass a given point. Now, you might be like, well, doesn't that depend on how fast it's moving? Yes, it very much does. Light, though, moves at the same rate. Every kind of light is always going to move at the same rate. I'm sure you've heard the speed of light. This is like how they talk about, you know, oh, the light from the sun takes like 8 minutes to get here. That's because there is a very well-defined speed at which all light travels. So in your exam equation sheet, I think I have this written as 2.998 times 10 to the negative, or 10 to the 8th. 3 is fine to use, but this is the speed of light in the units of meters per second. So if you had a wave that was moving past a given point, 3 times 10 to the 8th meters of that wave would pass that point every second. So 3 times 10 to the 8th meters. So you're talking about 30 million meters. So we could convert that into kilometers. So now we're going to be talking about closer to thousands. So 3 times 10 to the 8th divided by 1,000, and you know a kilometer is like approximately 2 miles, a little bit less, 1.6 maybe. Okay, so it's like, now I'm going to divide it by 1.6 to put it in miles. So it's like close to 200,000 miles, okay? 200,000 miles worth of light, like miles of light, is passing a point every second, okay? It's really fast. That's what I'm trying to get at. But it's consistent no matter what kind of light you're talking about. Okay? So if we have 2 different kinds of light, so let's look at the red and the blue now. And we're talking about how many waves are going to pass this point in a second. The longer wave, not as many are going to pass in a second, right? If we make the waves shorter, like more squished together, more of them are going to pass that point in a second. They're both traveling at the same rate. This one's just squished together, so more of them will pass by in that second. Okay, so we call that the frequency. So that's why the shorter wavelength is going to have a higher frequency, or more of them passing at a given second. The mathematical relationship that we use to describe this, everyone always thinks, oh, it's an equation. It's to plug numbers into. Equations are actually describing a concept. That is a very good thing to know when you're looking at any kind of science equation, even math equations too, but a science equation is trying to describe a concept mathematically. It's actually the reverse. We get the equation and then we figure out what it means conceptually, but you know, we're doing it this way because the equation's already been developed. So this is the equation. This is the Greek letter lambda, that represents wavelength. Okay, this curvy V, that is the Greek letter nu, and that represents frequency. And we're saying that when you multiply those together, this guy needs to be in meters. The wavelength needs to be in meters. The frequency is going to be the 1/seconds, or waves per second. When you multiply those together, they will be equal to the speed of light. If the speed of light is constant, that means if one of those goes up, the other one has to go down. Just like when we did PV, right? If pressure went up, volume had to go down. So it's the same thing here. They're inversely related. And that's just because inherently if you squish the waves closer together, their wavelength shorter, so more of them are going to pass a given point. So it's just like by the nature of what a wave is. That one goes up, the other one goes down. But what's nice is if someone reports a wave in wavelength, you can now convert it into frequency using this equation as well. Okay, so we'll do one of those at the end of class where I give you the, I think, wavelength and you convert it into frequency. Okay, we also said that there was this relationship, there's a relationship between wavelength and frequency, and there's also a relationship to energy, right? We said that the higher energy light is going to have shorter wavelengths, greater frequencies. So we need to now have an equation to describe how those are connected to energy. So that is on this one. So we're going to talk about all the details of this in a second. Right now we're just focusing in on this. Don't worry about the little n. We'll get to that in a second. Okay, so this is how we would calculate the energy. We would take the frequency times another constant. This guy's name was Planck. That's the constant that we use on the exam equation sheet. So you would determine the frequency and multiply it by this, and that would tell you the energy. So again, we'll do that at the end as well. I'll give you a wavelength. You'll calculate the frequency, then you'll also calculate the energy. The question is, though, is that energy of like this much of a wave, or that much of a wave, or a wave that fills the entire room? Like, those can't be the same thing, right? They're not. This really bothered a lot of early scientists. It took a long time before somebody, Einstein, again, came along and did an experiment. He actually didn't do it himself. There was someone else that did this experiment. It's called the photoelectric effect. We're not going to get into it. I'm not going to expect you to know what it is, except for the results of it. But if you want to, it's kind of interesting. You can go watch it. It's in your textbooks. You could go watch it or read about it. And it's what brings us to this more improved understanding of how we think of light. So in this experiment, they were like, I don't understand why, how can we calculate the energy if we don't know how much of the wave we're talking about? The results of this experiment made it look like waves the light didn't just come in these chunks of waves. Sorry, not chunks. In this stretch of waves. Is it a lot of wave? Is it a little wave? Is it, how do you divide those up? But it looked more like it came in chunks, in little packets of energy. Okay, so the analogy I like to use here is different types of balls. Like I'm going to talk about ping pong balls and steel balls. Those are going to be my two examples. So when I talk about packets of energy, I want you to think of the ball example. Okay, so we have different types of light. We have red light and blue light is what we were looking at before. And we know the blue light is higher in energy. So we're going to think of the blue light as a steel ball and the red light as a ping pong ball. So if I had the same chunk of energy, but different colors, and I threw them at something, the blue light is likely to have a lot more impact. Sorry, I'm trying to not use the right words yet. The steel ball is going to have a lot more impact. So think of like you throw them both at a window, right? The ping pong ball is not going to do anything. The steel ball is very likely going to break that window. That's because in this little packet of energy, it has more energy, even though it looks the same, like maybe it's the same size, it's moving at the same speed, it has more energy contained in it, okay? And we used to think of waves as just waves. Like in this experiment, the equivalent would be they just threw a bunch of ping pong balls and thought, well, shouldn't that break the window? It didn't, because like you guys know intuitively, like it doesn't matter if you throw a bunch of the ping pong balls, you have to throw one that has enough energy in that one thing. And that's when we started thinking of light as not just a wave, but as a little particle or a little packet of energy. So it's not that we stopped thinking of it as a wave. We still think of it as a wave sometimes, and sometimes it makes more sense to think of it as a little particle or a little packet of energy. We call them photons. And because they are little chunks of energy, so we have like, let's say we want, a bigger amount of energy, the way we would get that from a particular type of light is how many little packets of energy we use. So let's see. Yeah, I'm going to do this. Let's pretend that red light is like 1 unit of energy per packet, and blue light is 2 units of energy per packet. Well, if I want 100 units of energy, I'm going to have to use 100 packets of red light, right? 100 photons is the word. If I'm talking about blue light, I'm only going to have to use 50 photons to get that same amount. And the little packets that we divvy up, we say that those are quantized, meaning they come in a very discrete amount, and you can only get that amount in each packet. So blue light is always going to come in 2 unit chunks. Red light is always going to come in 1 unit chunks. You can't have 1.5 units of energy from red light. It just doesn't happen. That's what we mean when we say quantized. This is very connected to the ones and zeros that are used in computers, okay? It is either on or off. There's no in between. That is very much the same idea as you can have a little chunk of energy and another chunk of energy, but you can't have 1.5 chunks of energy. It's the same thing as you can have one atom or another atom, but you cannot have 1.5 atoms, okay? They come in little chunks. That's what we mean when we say they're quantized. It's really just a fancy word for they come in little chunks of whatever, chunks of matter, chunks of energy, on or off. The other word we use for this is digital. Digital means it's in little chunks. Analog means it's continuous. And a wave is considered continuous. If we were to look at a wave, we could be like, well, I can cut off this much of it, or this much, or this much, or this much, or that much, right? I can have it in any amount that I want. A wave would not be considered quantized. It would be considered continuous. Okay. So when we use this equation, the energy equation, that is going to give us the energy of one of these little packets or photons. Okay, so the N down there is telling you that is for one of those things. If you wanted to know the total, so we said, what if I have 100 packets? Then you would have to multiply it by that number, or 100. Okay, it's not very confusing. The other way to think of it is this is per photon, per little packet. So if I have 1,000,000 packets, I better multiply that number by 1,000,000 if I want the overall energy. Okay, this should start to be a little bit weird because light we always thought of as a wave. Matter we always thought of as a particle or a packet. So what we're doing here is we're starting to take the concept of matter and apply it to light. A few years after this, when we were having a hard time understanding the concept of an electron and how it behaved, this other guy, de Broglie, who doesn't get nearly enough credit, we always talk about Schrodinger when we talk about quantum mechanics, and de Broglie was fundamental in getting us started with quantum mechanics. He looked at this and was like, okay, an electron is a particle. And he's like, we're having such a hard time understanding how it works if we just think of it as a particle. He's like, do you remember how we were talking about light and we said it's a wave and then we started thinking about it like a particle? He's like, well, what about if we take this particle and we start thinking about it like a wave? So then we started modeling, this is at the heart of quantum mechanics, we started modeling the electron not just as a particle, but as a wave. Because we did the opposite for light, so why not do the opposite for electrons too? That is also what should blow your mind. You're like, what the heck? How can we think of a piece of matter like an electron as a wave? That doesn't make any sense, okay? It doesn't. This is at the heart of how things behave. They don't make any sense compared to what we're used to, okay? This concept of thinking of light and thinking of electrons as both of these things is called wave-particle duality. So you'll read that, I'm sure, multiple times in the textbook. It just means we think of it sometimes as a wave, we think of it sometimes as a particle, and that helps us to understand its behavior. Okay. So that you feel less scared and your brain starts working more normal, let's do some math, because that always feels a little bit better, I think. So we're going to calculate the frequency of a photon of red light, a packet of red light that has a wavelength, so this is wavelength, of 715 nanometers. Remember, 1 nanometer is equal to 10 to the negative 9th meters. Or another way of saying that is 10 to the 9th nanometers is equal to a meter. In the other unit, you guys needed to be really comfortable going back and forth between milliliters and liters. Here, you need to be comfortable going back and forth between nanometers and meters. That's because visible light is measured in hundreds of nanometers, and so it's a conversion we use frequently. So we're going to calculate now the frequency, that's what they want, using this equation. The speed of light is equal to wavelength times frequency. Then you're going to take that frequency and calculate the energy of a single photon by doing Planck's constant times frequency. And then finally, you're going to figure out the total energy by calculating the number of photons times the energy per each little photon. Okay, so take a shot at that. I'll give it a couple minutes. I'll write up the answers, compare them. So the reason why you have to convert this into meters is because the speed of light is in meters per second. Except for I still have 15th and you have 14th. Let me double check that I did it right. Does anybody else have 14th or 15th there on the frequency?
I have 16.
You have 16? Dang it, we don't need 3 different answers. Okay, 3 times 10 to the 8th. Oh, no, I didn't want that. I wanted the work, not the answer. 3 times 10 to the 8th divided by 7.15 times 10 to the negative 7. And mine is not putting it in scientific notation for me. I have the 14th still, and I wrote the 15th. It's 14th. I'll look at yours in a second if you want to see why it's not coming out right. Okay, that's 14. Okay, so frequency of a red light photon, energy of a single photon, 10 to the negative 19 joules, that's teeny tiny. energy of a mole, or 6.022 times 10 to the 23rd photons, that's about the energy to turn on a light bulb for a minute. Okay? So a mole of photons is about what it's taking to turn on that light bulb for a minute. I was actually surprised. I thought it was going to be a shorter amount of time for a light bulb. And actually it could be a little bit longer than that, maybe even like 2 minutes. Okay? Yes, we're going to do a little math, not a ton. All right, I'll see you guys on Wednesday. Yeah, it's because of the parentheses.
Oh, I
So,
don't know.
yeah, so you gotta put, anytime you have like a times 10 something on the bottom, you've gotta put parentheses.
Got it, okay, thank
Yeah.
you.
Hi.
I'm gonna watch the thing, obviously, but
Mhm.
why, like, up here?
Yeah, so that should be the other way around. It should be nanometers on the bottom. Did I
Okay.
write it as meters? Oh, yes, it was me.
So, okay, I thought maybe like it was opposite.
No, you're good. It was just the units. The numbers are right. 1 nanometer, 10 to the 9th meters. All good.
Okay, and then, like, to like get the concept again,
Uh-huh.
where did you say we could find that?
So on the textbook, let me pull it up and see if I can find exactly where, but it's in chapter 8. And I'm hoping that he has a good video of this. Khan Academy is another good resource. If you look at anything that's in there like AP Chem or freshman chem, like college chemistry, it's reliable. Ta-da. Okay, that is probably the only one that applies to today.
Okay.
So you could read the chapter, but I would say that video is going to give you a decent overview.
It's the numbers that messed me up.
Oh, okay.
I had you up until you started plugging in numbers.
Oh, well, that's surprising because I thought the other part was harder. So there's other examples here too. Like in this one, you're doing the same thing, solving for frequency.
Okay.
So it's just another very similar, but another example. There's probably another one down here.
That's 8.2.
Yeah,
Okay.
that's a concept one though. But yeah, this is in section 8.2.
Thank you.
Yep. Okay. 3 times 10 to the 8th. Oh, it's times 10 to the negative 7. So it's 10 to the negative 9th nanometers, but it was 715. So if you had written 715 e negative 8 or negative 9, that would have worked. Or if you write 7.5 times 10 to the negative 7, that would have worked.
Okay.
Yep.
Okay. That makes more sense.
Yep. And that is 2 decimal places, so it definitely works.
Thank
All good?
Yeah.
Okay. Hi.
I wanted to ask you where I can watch the videos at.
Yeah. So, oh, for mine?
Yes.
Yes, I think it's just Chem C, like C for Carrie, but I know on Blackboard there's a link. So if I have my thing logged in, I'll show you real quick.
I need to start watching.
That's fine. You're like, stop talking so fast. All right. Okay. So on Blackboard, course details. There's an exam recommended. Oh, come on. I know it's in there. Should be, oh, it's on the syllabus. That's why. Okay. So if you go to course details, then you go to course syllabus, then you open it, then it's right there.
Okay.
And it's right there, chemical C. So that's the, what is that called? Like the channel name?
Mm-hmm.
Chemical C.
Awesome. Great.
Yep.
Thank you.
Mm-hmm.